Hello, everybody. My name is Selcuk Uluagac. Thanks for the introduction, Brandon. So the title of the presentation is 6thSense, context-aware sensor-based attack detector for smart devices. In fact, this is my PhD student's work, Amit's work, but he couldn't make it because of the visa problem. So I'm presenting on all the authors' behalf, basically. So there are 4 sections in the presentation. In the first part, I'm going to be introducing and talking to you about the sensors and how we are using sensors in different applications in smart devices. And the second part, we're going to be focusing mostly on the existing sensor management systems, how they handle the sensors, how they utilize, and then how they could be abused, exploited. And our observations that we have in designing the 6thSense framework. And then I'm going to be talking to you about the different detection approaches that we have in the 6thSense framework. And then I will be talking to you about the evolution of the framework. Finally, I will conclude and then present you the future work. So when we look at the devices today, we see that sensors are everywhere, from wearables, medical devices, smart homes, smart city, military applications. We see that all the devices come with different sensors. And in fact, it's hard to find a smart device today without any sensor on it. And even further, it's even harder to find any device, any smart device with only one sensor on it. They usually have more than one sensor. So we can compare the sensors to the sensing organs in our bodies, actually, in terms of the functionality. So as sensing organs are really crucial in our functionalities and in our operations, day-to-day operations, it's the same way in our smart devices. Motion sensors, environmental sensors, and position sensors are all critical in our applications. The sensors make the applications smarter and more useful, and they become cooler, so we enjoy them. So if these are exploited or if these are abused, then these critical functionalities and all these smart things are also impacted. So while these sensors are useful, the usage of sensors actually introduces new sensor-based threats. This has been explored by other researchers as well, from keystroke interference, information stealing, to denial of service, to drones recently, triggering malware, and location interference, eavesdropping, transferring malware, exploiting hardware. So different works have shown different threats for smart devices with sensors. Abusing or exploiting the sensors. In fact, just recently, you may have heard of from US ISCS CERT that different accelerometers are actually vulnerable for malicious purposes. So we are motivated to look at this problem in this work. So why there is such a problem? We first think that the users are not really knowledgeable about the threats yet, and they don't know about the consequences, even if they know it, and if they give any permission, for example, to a sensor on a smart device. And more importantly, we see that the existing sensor management systems in different operating systems really do not really handle the sensors very well. There is currently not effective and comprehensive security solution or mechanism available yet. So we are motivated to solve this problem in this work. So as a summary, our work is basically introduces the design of a context-aware sensor-based attack detector, which is called 6thSense. The 6thSense, with 6thSense, we evaluate our framework with different users, with 50 users, and we have a high detection rate with minimum system overhead. We also test it against different malicious apps. So now let's talk about the technical details of this work and how it is, in ways different, or how it complements the existing body of work. But let's focus on first the existing sensor management systems. When we look at the existing sensor management systems, we see that they are all permission-based systems. However, they are only covering certain sensors. Not all sensors are covered. For instance, here in an Android app, different apps access the sensors through the hardware application layer. Apps ask for user permission for sensors at the time of installation. For example, you install an app, and the installation is going on, and the installations ask you, hey, can I access to this microphone, GPS, camera, etc., etc. You give permission because you want to install the app, but at the end, when you give permission to a certain set of sensors, we see that it's only enforced on certain sensors. For example, gyroscope and accelerometer is automatically assumed to be given access when you give access to microphone or camera. So, as other researchers and other speakers also noted in their talks, no user control exists after actually you give the permission. And you don't know how the sensors are actually used after you even give the permission. So this is the core of the problem in the existing sensor management systems. And we are trying to solve this problem. So in our threat model, so we have three different threats. So we try to formalize, and so the things that can go wrong. And there are three things that can go wrong. One is you can trigger, as with a malicious app, a malware that exists on the smart device. You could use basically a sensor, a light sensor, or a motion sensor that may have been already existing on the smart device. The other threat is information leakage via sensors. I'm saying sensors because in all these threats, you can actually use either one sensor or you can use more than one sensor to be able to do your malicious activities. So you can record. You can, for example, record a certain sensitive data, and then you can further transfer that sensitive data to outside parties. The last threat is that we consider in our threat model is stealing information via sensors. You could exploit the sensors to capture information on a device or on a device or a nearby device. So based on these different threat models, we created 3 different malicious apps, and then we tested the effectiveness of these, whether these threats are recognized by current tools, and we scanned it with the virus total. And our apps, malicious apps, have not been recognized by virus total. And we use these basically malicious apps in our evaluation, as I'm going to discuss later. So there are several important things to understand before I introduce the design of 6thSense. So there are several observations, in fact, that when we look at the devices, smart devices, how the sensors are utilized. So let's assume that you're walking, talking, or sitting down, or doing different activities with your device. When you look at a device, a different number of sensors are activated. Like, for example, in walking, accelerometer, gyroscope, light, and GPS might be activated. In talking, accelerometer, gyroscope, proximity, and audio sensors might be activated. While sitting, light and audio might be activated, and 2 of the sensors may be similar to the previous set of sensors. So for each user task and activity, a specific set of sensors remains active. And for this, sensors can be considered as codependent entities for each user task and activity. So by observing the active sensors for a task or activity, it's possible to differentiate between benign activities and malicious activities. And then we call this sensors are task-wise dependent. And this is one of the features of our design, 6thSense. So let's look at an example and another important term for our design, which is context awareness. So when you're walking at state 1, you may have certain number of sensors activated. In state 2, different set of sensors activated. And state n, you may have, again, different number of sensors activated. So we tested this and we observed this, and then our design is basically considering all this differing changes. So this is what we call a walking context. So when you're walking, it's not always 3 sensors are activated. You may be activating, the device might be activating different number of sensors. But overall, when you walk, you have a context, and then we are capturing in 6thSense this walking behavior, and this is our context. This is the design, one of the features of the important features of the design. So other important observations that impact the design of 6thSense is sensor sampling. Different sensors have different sampling frequencies, so sensor data should be sampled according to the sensor frequency. And high precision sensors, because smart devices have different sensors from different manufacturers, and they have differing frequencies to capture the data and process a large volume of data. So they should provide fast computation for large data set. Some sensors capture more data than the others. And as I also hinted at the beginning, modern smart devices come with different set of sensors, and any framework should consider all the sensors to build a context-aware model. So these are all basically the fundamental features of our 6thSense. So 6thSense has basically 3 basic steps. First, the data is collected by the sensors, and by permission imposed sensors and no permission imposed sensors. Then data is processed, organized. Basically we organize the collected data, and we do the sampling of the sensor data, and then we build the task activity context for the data analysis from raw data, and then we do the analysis. So in the analysis part, we deploy the different detection techniques. Our detection techniques has 3 different mechanisms we utilized. And these are all machine learning based techniques. And one is Markov Chain based, the other is naive Bayes, and then the other is other machine learning techniques. We wanted to utilize these different techniques because they were fast in computation, and their computation requirements met by devices with low processing capacity, minimum training time for large training data. They could process large data set in short time. They could support supervised learning, and it was easy to implement, and it was suitable for sensor codependence. So let's look at how we actually utilize these different detection mechanisms with the context awareness. So for Markov Chain, what we did and what the 6thSense does is that, so we look at what sensors are activated at a certain device state. Let's say at state 1, and a certain number of sensors are activated. We grab this as a state. And then at state 2, then we have different set of sensors are activated, and that becomes state 2. And so on, we go all the way up to device state n. Then we feed this into our Markov Chain model and train it, and then we test it, and then we collect the results. So in a naive-based detection technique, it's similar. Obviously, naive-based model is very simpler version of, it's a very simple detection technique, but we wanted to incorporate and we wanted to see how it's effective, whether it's effective or not, and I'll share the result later. But here, what we did, we also, again, stick to the same problem, stick to the same principle. All device states are independent, and under each device state, the features where different sensors are activated or not activated are considered. So again, we feed this into our model, different context, and then we built the model accordingly. Then, as a final detection method, we wanted to use a Weka-based machine learning algorithms. We simply use different machine learning algorithms directly from Weka, such as PART, logistic function, J48, logistic model 3, multi-layer perception, which is artificial neural networks. And then we did a 10-fold cross-validation to test the framework. Basically, we made sure that we have effective results. So let me share. Let's share the results with you. And in the performance evaluation, we collected data from 50 different users. We focused on total of 9 different activities. These activities were basically categorized into generated text and then user-related tasks. 75% of the data used for training and 25% of the data is used for the test. So these are the performance metrics that we used. We used recall, false negative rate, specificity, false positive rate, accuracy, F-score, ROC, PRC curve, and then also we look at the performance overhead. As I said, we also had our malicious apps. So we tested the efficacy, basically, of our system against the, considering these malicious apps. So here are the results with the Markov Chain based detection. As you see here, we have really good results with the Markov Chain model. Basically, here, number of consecutive malicious states means that we have n states for the Markov state, and then each state includes different number of sensors are activated. And so when malicious app is going on, when something bad is going on, how many times that malicious state is happening, basically, consecutively. So we wanted to look at how many times that a user, when it's doing its activity, it could differ from the benign activities. So we were really happy with the results we had. And you look at the ROC and PRC curves. So with the ROC curve results are on the left, and then the PRC curve results are on the right. So as you see, our results are really very promising. We also wanted to look at the PRC curve because we were using 75% of data for training and 25% of data for testing. So we didn't want to have a situation where we are having an imbalanced data set. So we wanted to make sure that we have good, effective results in different cases. So these are the results for the naive-based model. Naive-based model results are not as high as the Markov Chain-based model. I think it's naive-based being naive, I guess. But it's still effective to some extent. It's 80% around. The ROC curve results and PRC curves results are also indicates good and very promising results. But it's not as high as the Markov Chain-based model, detection model. Finally, as I said, we utilize Weka and to be able to see the effectiveness of the framework in recognizing the malicious apps. So LMT was the highest in terms of the results. So here we compare the LMT, naive Bayes, and Markov Chain with different performance metrics. We wanted to look at different performance metrics because accuracy, if you look at accuracy only, that may be misleading. So we wanted to look at the F-score, which is the harmonic mean of the precision and recall. And so we were really happy. The LMT and Markov Chain were really giving good results. Then we want to look at the performance evaluation of the overhead of the data collection and data analysis phases. On the top left, you see the CPU usage. And on the right, you see the RAM usage, memory usage, and the disk usage, and then the power consumption. as you notice here, no permission-based imposed sensors and permission-imposed sensors have differences in their overhead. The reason is that permission-imposed sensors are basically requires less effort to be able to get the results, but the non-permission imposed sensors requires more effort to be able to incorporate into the framework. Power consumption-wise, the system is not really, it's only providing minimum overhead. Considering the different batteries of smart devices. Then we look at the data analysis part. The CPU usage. At this time, we look at different, how different detection algorithms are performing. Markov chain and is utilizing the least CPU, and LMT is second, and naive-Bayes is the highest. And for the RAM, again, Markov chain is good. For the disk usage, they are almost the same. And for power consumption, Markov chain is really good. Overall, we think that Markov chain was really giving us good results in our detection framework, and was really also understanding the fundamental design of 6thSense, which is context awareness, and then task codependence. So let me summarize. In this work, we introduced a novel context-aware sensor-based attack detector. We utilized different machine learning techniques, including Markov chain, naive-based, and other machine learning algorithms, to develop the framework and incorporate into the framework. We tested the design with different users, 50 different users. The results really, show us a high detection rate with minimum system overhead. As a future work, we plan to enhance this work for other small sensor enriched handheld devices like fitness band, smart lock, etc. And I'd like to also acknowledge the NSF's support for this work, their generous support. So here are the references, and so we have one demo available. If you're interested in, you can go to this website and take a look at how this attacks could work in real time, and these are my collaborators in the work. Amit unfortunately couldn't be here today, so with that, I'll be happy to take any questions you have, and thank you very much.
Step on up to the microphone.
I'm Yongde Kim from KAIST. If it is within the context, how do you detect sensor spoofing attacks?
I'm sorry, I didn't get the question.
So if some spoofing is within the context, how do you detect spoofing attacks?
That's a good question. For that to happen, it's not that easy, because it has to, for our model, it has to be really fake and fool the system in very sophisticated manner, because the design of the Markov detection model considers up to several consecutive malicious states, and for naive-based, it may be fooled easily, but the Markov chain, we have really good results with that detector, Markov chain based. So it would be harder, but of course, I'm sure we can, anything is, breakable, I think,
Phoebe Rouge from the FTC. I have a question about as far as how you map the different, so you have a set of context states, how you map that to particular tasks. Like, do you ask the user, what are you doing right now? Or sort of like, how do you know that the user is doing a certain activity when you are measuring these states?
So what we did, we had 50 different users, and we basically collected the data in a controlled setting, and we said that, hey, these are 9 activities that you need to do, and basically they did walking, sitting down, playing with the game, etc., etc. So when they were doing that, we collected the data. So it was in a controlled setting. So
Well,
yeah.
I was thinking sort of like in the actual then test. Is it the same, basically the same process then?
I'm sorry?
So like I can see where that's sort of like training the model. Then when you're actually testing the model, do you have the same
Yes.
thing?
Basically, yeah, we split the data 75% and 25%. But we made sure that, like, that's why we did so many things like 10 cross-validation and all sorts of random things, on the model. Make sure that it's really as reflective as a correct behavior of a malicious behavior. Yeah, it's a good question. Yeah.
I'm from from Postec. Thank you for your good talk. My question is that, as I understood, the sensor values are numeric values, and you use the binary status, right?
I'm sorry?
The sensor values are numeric values, but
Yes.
you use the binary status, right?
Exactly.
So,
yeah, that's why the basically some of the sensors
Yep.
were giving us only value,
Yep.
and some of them only were giving only binary status. The ones that were giving the binary, it was easier to access and get the data. And that's a good catch. Yeah.
So, in my opinion, the sensors such as gyroscope or accelerometers show so unstable values, and so it is difficult to catch the accurate values. But I wonder how you determine the status of the sensors.
Yeah. So we basically look at, as you noted,
Yep.
whether the binary status, whether it's being used or not.
Yep.
We didn't look at hey, what is the value here, and what is the value here, whether it makes sense. Accelerometer is now showing this, accelerometer is giving this, etc. etc. We didn't look at that. Yeah, we looked at all of them in a holistic manner, and then in a context, basically. And then we were also cognizant of the fact that some of the sensors might be, even if you're doing walking, some might be activated and some might not be activated all the time, basically.
Okay, thank you.
Yeah.
Okay. So I actually had one quick question, which is, so you created sort of 3 malicious apps to test sort of what the detection rates were. Did you try submitting these apps to the Google Play Store?
No.
Okay.
Yeah. We only tested with the VirusTotal.
Okay.
And make sure that it's not recognized basically by the scanner, current malware scanners, and it was good enough for us to basically to verify that it's not recognized currently with anything, basically. And plus, there is not any current malware for sensors yet, to the best of my knowledge. Yeah. Okay.
I had a question. So
Yeah.
if I understand your system correctly, a user who wants to use this has to do some training with apps on their phone to teach 6thSense about the sensors, and then they have protection. What happens if the user already happens to have some bad apps on their phone when they're doing the training, so that the training is actually using the sensors it shouldn't? Have you thought about that at all?
No, we haven't thought it. That's a very good question. Yeah. Thank you.
All right. Let's thank our speaker again.
Yeah.